On a clear night, far from the lights of any city, you can see it. Not all of it, not even most of it, but a band of faint light stretching from one horizon to the other, a river of stars so dense that individual points blur into a continuous luminous haze. Ancient light, accumulated across distances so large that the human mind cannot genuinely hold them. This is the Milky Way, our galaxy, the structure that contains our sun, our solar system, every planet we have ever visited, every human being who has ever lived. At the very heart of the Milky Way, hidden from direct optical observation by roughly 25 magnitudes of intervening dust, visible only through radio waves, infrared light, and X-rays, there is a place unlike anywhere else in our galaxy. At the very heart of the Milky Way, hidden from direct optical observation by roughly 25 magnitudes of intervening dust, visible only through radio waves, infrared light, and X-rays, there is a place unlike anywhere else in our galaxy. And at the center of all of it, at the precise gravitational focus of everything, something dark, something massive, something that does not shine. A black hole 4,000,000 times the mass of our sun. For 20 years, this black hole, named Sagittarius A, was a model of predictable behavior. It flickered, it flared, it varied within a known range. A sleeping giant that occasionally stirred but never truly woke. In 2019, something changed. The flickering became a blaze. The black hole brightened by a factor of 75 times its normal infrared luminosity in less than 2 hours, reaching a peak that fell entirely outside the range that 20 years of observation had defined as possible. Something strange is happening at the center of the Milky Way. The Milky Way is a barred spiral galaxy. Its stars, gas, and dust are organized into a flat rotating disk roughly 100,000 light-years in diameter. At its center, instead of a simple hub of increased stellar density, there is an elongated bar of stars stretching roughly 27,000 light-years from end to end. The spiral arms connect to the ends of the bar, winding outward into the disk. The Sun sits approximately 26,000 light-years from the galactic center, in a region called the Orion Arm, an ordinary star in an ordinary position in a galaxy that contains hundreds of billions of others just like it. The galactic center itself is, by contrast, an extraordinary environment. The central molecular zone extends roughly 1,000 light-years from the galactic center, containing tens of millions of solar masses of dense molecular gas. Within it lies the nuclear disk, roughly 300 light-years across. Within that, the nuclear star cluster, one of the densest stellar environments in the Milky Way, with a stellar density millions of times higher than the solar neighborhood. And at the center of the nuclear star cluster, at the precise geometric and gravitational center of everything, sits Sagittarius A. The most famous of the stellar populations surrounding Sagittarius A is the S-star cluster, a group of massive, hot, young stars on tight elliptical orbits directly around the black hole. Their orbital periods range from a few years to a few decades. The most precisely monitored, S2, has a 16-year orbital period and reaches speeds approaching 3% of the speed of light at its closest approach. Beyond the S-stars, there are clockwise rotating disks of massive young stars that should not exist in the tidal environment of a supermassive black hole, but do. The paradox of youth, one of the outstanding problems of galactic center astrophysics. The galactic center is invisible. In the most literal optical sense, the light from the galactic center, in the wavelengths that human eyes can detect, never reaches us. It is absorbed completely by the intervening dust. Between the solar system and the galactic center lie roughly 25 magnitudes of visual extinction, a source as bright as the sun, placed at the galactic center, would be completely undetectable to the human eye from Earth, not dim. Simply gone, absorbed before a single photon of visible light could traverse the full distance. The first breakthrough came with radio astronomy. Radio waves, photons with wavelengths measured in centimeters and meters, are not absorbed by dust in the same way. They pass through the interstellar medium largely unimpeded. When radio surveys of the galactic center were conducted in the 1950s and 1960s, they revealed a bright, compact radio source at the precise center of the galaxy, later named Sagittarius A, and later still resolved into Sagittarius A*, the object we now know to be the supermassive black hole. The second breakthrough came with infrared astronomy and then adaptive optics, allowing ground-based telescopes to see through the dust and achieve space-like angular resolution. Together, the four observational windows, radio, infrared, X-ray, and millimeter radio, provide a comprehensive multi-wavelength picture of the galactic center. Each wavelength probes different physical conditions, different spatial scales, different components of the complex environment surrounding the central black hole. This observational infrastructure, built up over 50 years of technological development, representing the work of thousands of scientists across dozens of institutions, is what makes it possible to know that something is happening at the center of the Milky Way, and it is what makes it possible to begin understanding what that something is. Sagittarius A* was not discovered all at once. It accumulated, first as a radio source, then as an infrared puzzle, then as a gravitational anchor, then as a directly imaged object, through a progression of increasingly precise observations spanning 5 decades. The case for a massive compact object at the radio position of Sagittarius A* was first made from measurements of stellar velocities in the early 1990s. Individual stellar velocities in the central few light years were measured to be extremely high, hundreds of kilometers per second, implying a concentrated mass of millions of solar masses within a small volume. The orbital measurements settled the question definitively. The star S2, reaching its closest approach in 2002 at a distance of approximately 120 astronomical units from the radio position, provided the most stringent constraint. The mass must be concentrated within a sphere smaller than 120 astronomical units in radius. A mass of 4 million solar masses concentrated within 120 astronomical units has a density far exceeding the limit for any known stable cluster of stars or stellar remnants. The only known class of object with the required mass-to-size ratio is a black hole. The mass of Sagittarius A* has been measured with increasing precision as more complete stellar orbits have been obtained. The current best estimate is for 0.154 million solar masses, with a fractional precision of better than 0.5%. The distance from the Sun to Sagittarius A*, the fundamental scale of the Milky Way, has been measured to 8.178 kiloparsecs, approximately 26,674 light-years, with an uncertainty of about 0.013 kiloparsecs. What makes Sagittarius A* uniquely valuable scientifically is the combination of proximity and mass that allows it to be studied with a resolution impossible for any other supermassive black hole. The night of May 13, 2019, began like any other observing run at the Keck Observatory. The telescopes opened as darkness fell over Mauna Kea. The adaptive optics systems locked on. The infrared cameras began accumulating photons from the galactic center. The scientists monitoring the data settled in for what they expected to be a routine night of monitoring, adding another set of observations to the 20-year baseline they had been building since the late 1990s. Tuandu, a research scientist at UCLA, was among those monitoring the incoming data, and then the numbers started coming back wrong. The photometric measurement of Sagittarius A* was too high. Not catastrophically, immediately obviously wrong. but wrong in the way that an experienced data analyst recognizes before articulating why, a value sitting outside the range that feels familiar. A number that prompts a second look not because it screams instrumental error, but because it simply doesn't fit the accumulated intuition of 20 years of watching this source. To check the calibration, the comparison stars looked normal. He checked the sky subtraction. He looked for cosmic rays on the detector. He found nothing anomalous. The number was still too high. As the night progressed, the picture became impossible to dismiss. Sagittarius asterisk was brightening, building, sustained, climbing with each successive image. By the time the source reached its peak brightness, it was producing approximately 75 times its median infrared luminosity in the Kp band. 75 times, the brightest state ever recorded in 20 years of systematic monitoring. After the peak, the brightness slowly declined. But it did not decline back to the historical baseline. The brightness settled at a level above the pre-flare average. And in the weeks and months that followed, the elevated baseline persisted. The paper documenting the observation was published in the Astrophysical Journal Letters in August 2019, an unprecedented bright flare of SGR*. The spectral index during the peak was different from typical flares, steeper, implying either a harder electron energy distribution, a stronger magnetic field, or a different spatial geometry. The 2019 event was not simply a large flare, it was a different kind of activity. It occupied a region of physical parameter space that was not an extrapolation of the known population of historical flares. It required either a distinct physical mechanism or a dramatic enhancement of a known mechanism operating in a different regime. The material supply for Sagittarius asterisk comes from approximately 24 massive stars, whose powerful stellar winds continuously shed material into the galactic center environment. These winds collide, shock heat, and some fraction of the resulting hot gas is captured by the gravitational pull of the black hole. This captured gas forms an accretion flow, a rotating structure of plasma that surrounds the black hole and slowly loses angular momentum, allowing material to spiral gradually inward. At the accretion rates relevant to Sagittarius asterisk, this flow is not a thin, bright, efficiently radiating disk. It is a thick, hot, geometrically extended torus of plasma, a radiatively inefficient accretion flow, or RIAF. In a RIAF, the plasma is so sparse that collisions between ions and electrons are rare. The ions carry most of the thermal energy but cannot efficiently transfer it to the electrons. The electrons, which produce the observable radiation, are therefore significantly cooler than the ions, and radiate only a small fraction of the available energy. The result is an accretion luminosity many orders of magnitude below what would be produced by the same mass accretion rate in an efficient thin disk. Sagittarius asterisk radiates only about 10 to the minus 9 times its Eddington luminosity. By the standards of actively accreting supermassive black holes, it is essentially silent. The magnetic field near the event horizon reaches the highest values in the entire accretion flow, forced to concentrate as the plasma descends to smaller radii. Near the innermost stable circular orbit, the magnetic field strength may reach values of hundreds to thousands of Gauss. In this highly magnetized environment, magnetic reconnection becomes the dominant energy release mechanism. When magnetic field lines of opposite polarity are forced together, they annihilate, releasing magnetic energy explosively. The electrons accelerated in these reconnection events spiral around the field lines and emit synchrotron radiation, like the infrared and X-ray flares we observe. For the May 2019 flare to be 75 times brighter, the physical conditions must have been substantially different. The magnetic field stronger, the reconnection region larger, the electron acceleration more efficient, or all three. Sagittarius A does not exist in isolation. It is embedded in an environment that is continuously changing, stars on elliptical orbits delivering enhanced material at certain points in their orbits, dusty objects on close approaches that may be partially disrupted by tidal forces, stellar winds that vary with the evolutionary state of the stars producing them. Two objects, in particular, command attention in the context of the 2019 flare. The first is G2. When G2 passed through periapsis in 2013-2014, the Galactic Center community watched with a coordinated international campaign. And Sagittarius A did almost nothing. The continued detection of G2's core emission, maintained at a compact, essentially stellar point source, after periapsis demonstrated that G2 had survived essentially intact. It was not a pure gas cloud. It had a compact stellar core, almost certainly a stellar merger product, surrounded by an extended gas and dust envelope. The stellar core survived the tidal encounter. The outer envelope was partially disrupted. But the outer envelope did not simply disappear. It was put on orbits of varying angular momenta, bound orbits that would return portions of it toward Sagittarius * on timescales of years after the periapsis event. The second object is S2, S2 reached its closest approach to Sagittarius * in May 2018, one calendar year before the unprecedented flare. As a massive B-type star with a powerful stellar wind, S2 deposited enhanced wind material into the galactic center environment at a distance of only 120 astronomical units from Sagittarius * at periapsis. The material from S2's periapsis wind would be delivered to the inner accretion zone on a timescale of months to a year, placing its arrival in the timeframe from late 2018 to mid-2019. Coincident with the onset of elevated activity, gravity operates at the Very Large Telescope Interferometer in the Atacama Desert of Chile. It combines the light from all four of the VLT's 8.2-meter unit telescopes into a single interferometric instrument with an effective baseline of 130 meters. The angular resolution this achieves, approximately 4 milliarseconds in the near-infrared, combined with positional centroid measurements at the 10 to 20 microsecond level, is sufficient to resolve spatial structures at the scale of a few Schwarzschild radii around Sagittarius *. Gravity's primary science included the measurement of stellar orbits with unprecedented precision, providing the most accurate measurements yet of S2's orbit and the first direct detection of general relativistic effects in stellar orbits around a supermassive black hole. During bright infrared flares of Sagittarius *, gravity detected orbital motion of the flare emission itself, the centroid of the flare's emission moving in a pattern consistent with circular orbital motion around the black hole, with a period of approximately 30 to 45 minutes. This is the orbital period of material at the innermost stable circular orbit around Sagittarius *, the smallest stable orbit possible, at 3 Schwarzschild radii from the event horizon. We are watching material orbit a supermassive black hole at 30% of the speed of light, in real time. The picture that emerges from the gravity observations is of localized, compact plasma structures, called hotspots, that form near the ISCO through magnetic reconnection events and orbit the black hole for 1 to several orbital periods before fading as the accelerated electrons cool. Comparing the properties of flares observed before and after 2019 suggests that the post-2019 flares are characterized by harder electron energy distributions, more high-energy electrons relative to low-energy ones, consistent with a more strongly magnetized inner accretion flow. The gravity data thus provides independent evidence, from direct observations of the near-ISCO environment, that the magnetic field configuration of the inner accretion flow has changed since 2019. On May 12, 2022, the Event Horizon Telescope collaboration held a coordinated global announcement at 6 simultaneous press conferences across 4 continents. The image they revealed showed, for the first time, the direct visual evidence of the black hole at the center of our galaxy, the shadow cast by Sagittarius A on the glowing ring of plasma surrounding it. The dark region where the gravitational pull was so extreme that photons could not escape. The ring's diameter matched the theoretical prediction for a black hole of 4.154 million solar masses within the measurement precision. The image was, in the most literal sense, a photograph of the edge of a black hole. Imaging Sagittarius A was substantially more difficult than imaging M87 *, the black hole the HT had imaged first in 2019. Sagittarius A's orbital period is approximately 30 minutes. During an 8-hour observation, the source completes 16 full orbits. The plasma structures change completely multiple times during a single night's observation. The EHT collaboration solved this by developing new image reconstruction algorithms specifically designed for a time-variable source, producing an image that represents the time-average structure of the accretion flow, the mean appearance of SGR* over many orbital timescales, the polarization of the ring emission, the orientation of the electric field oscillation in the radio waves carries information about the magnetic field configuration in the emitting region. Subsequent EHT polarization observations revealed a partially ordered magnetic field structure near the event horizon, consistent with a magnetically arrested disk state. A regime in which the magnetic flux accumulated near the event horizon is strong enough to periodically arrest the infall of material and organize the field into a more coherent structure. The MAD state is associated with episodic large-scale magnetic reconnection events, exactly the kind of events that would produce the unusually large and spectrally distinct flares observed in 2019 and subsequently. The magnetic reconnection events that produce infrared flares from Sagittarius A are energetic enough to also produce X-ray emission. Large infrared flares are typically accompanied by X-ray flares, correlated brightenings in both wavelength bands occurring in close temporal proximity. The relationship between the infrared and X-ray flare properties, their relative brightnesses, the timing of the correlation, the shapes of the light curves, provides diagnostic information about the physical conditions in the flaring region that neither wavelength alone can provide. The primary X-ray monitoring of Sagittarius A has been conducted by the Chandra X-ray Observatory since its launch in 1999. The coordinated multi-wavelength monitoring campaigns, combining Keck infrared observations with simultaneous Chandra, XMM Newton, and Nuster X-ray coverage, plus radio monitoring from the Very Large Array, have produced the most comprehensive physical characterization of Sagittarius A flare events ever achieved. Since 2019, the X-ray behavior of Sagittarius A has also shown signs of elevated activity consistent with the infrared monitoring data. The rate of large X-ray flares appears to have increased relative to the pre-2019 baseline. The elevated activity is not just infrared. It is systemic, present across wavelengths, confirmed by independent instruments, pointing to a global change in the accretion state. The 2019 flare is significant in the context of 20 years of monitoring. But placed in the context of the Milky Way's full history, it is barely a whisper compared to the activity that Sagittarius A has been capable of in the past. In 2010, a team analyzing Fermi Space Telescope data discovered something that had been hiding in the diffuse gamma ray background. Unnoticed because no previous instrument had the combination of sensitivity and sky coverage needed to see it. Above and below the galactic plane, centered on the galactic center, two enormous lobes of gamma ray emission, roughly spherical structures extending approximately 25,000 light-years above and below the disk, the Fermi bubbles. Understanding what produced the Fermi bubbles has been one of the central challenges of galactic center astrophysics since their discovery. Two broad classes of explanation have been proposed. The first invokes a past active phase of Sagittarius A, jets or outflows from a much more luminous black hole inflating the bubbles over millions of years. The second invokes intense star formation activity in the galactic center region. Most current models favor the AGN explanation because the detailed morphology of the Fermi bubbles matches more naturally to a compact, powerful energy source, exactly what an active Sagittarius asterisk would provide. The implication: Sagittarius asterisk was millions of times more luminous in the past. What the Fermi bubbles and the X-ray reflection measurements together establish is this: Sagittarius asterisk has been much more active in the past. Its current near-dormant state is not its natural condition on cosmic timescales. The 2019 flare and subsequent elevated activity are, in this longer view, not bizarre anomalies but the most recent manifestation of the episodic activity that has characterized Sagittarius asterisk throughout its history. What makes the current episode scientifically extraordinary is not its existence. Such episodes have presumably occurred many times before. It is that this episode is happening while we have the instruments to observe it in real time. The observable universe contains an estimated 2 trillion galaxies, each harboring at its center a supermassive black hole whose mass correlates with the properties of its host galaxy in ways we are only beginning to understand. The Milky Way occupies a specific and interesting position in the population of barred spirals. Its stellar mass of roughly 50 billion solar masses places it in the upper half of the galaxy mass function. Its central black hole mass of 4.15 million solar masses is consistent with what would be expected from the well-established M-sigma relation, the correlation between black hole mass and host galaxy's central stellar bulge velocity dispersion. This correlation implies a deep connection between the growth of a galaxy's central black hole and the growth of the galaxy itself. The Milky Way's central black hole is in a particularly quiet state compared to the full range of activity seen in galactic nuclei across the universe. At the extreme of activity are quasars, powered by supermassive black holes accreting at near their Eddington limits, outshining entire galaxies. The most luminous known quasars have black hole masses of billions of solar masses and luminosities 13 orders of magnitude above the current Sagittarius asterisk. Sagittarius asterisk is the most accessible member of the dormant end of this distribution. Its proximity makes it possible to study low accretion supermassive black holes with resolution impossible for any more distant system. Does what is happening at the center of the Milky Way pose any threat or consequence for Earth or for life in the solar system? The answer, for any time scale that matters to human beings or to biological life on Earth, is unambiguously no. The galactic center is 26,000 light-years away. The May 2019 flare, at 75 times the normal infrared luminosity of SGR**, was completely undetectable from Earth without purpose-built infrared instruments pointed at the galactic center. It had no measurable effect on Earth's electromagnetic environment. This is not a close call for the radiation from the galactic center to pose any practical concern for Earth. Sagittarius * would need to increase its luminosity by many orders of magnitude, approaching the luminosity of a full AGN or quasar, and sustain this luminosity for extended periods. Such a transition is not predicted by any current model on timescales relevant to human civilization. The physical mechanisms that could produce a dramatic increase in Sagittarius * accretion rate are not anticipated in the near future. There is one channel through which galactic center activity could affect Earth on very long timescales: cosmic rays. But these effects operate on timescales of millions of years and are subtle. The honest and complete answer is thus nothing happening at the galactic center in the current episode of elevated activity has any consequence for Earth, for life, or for anything that matters on any timescale shorter than many millions of years. What is happening is scientifically fascinating. It tells us profound things about the physics of black holes, about the history of our galaxy, about the connection between central black holes and their host galaxies. But it is happening 26,000 light-years away. The universe is large enough that its most extreme phenomena can be observed, studied, and understood without posing any threat to those doing the observing. The scientific program motivated by the 2019 flare is being pursued with instruments currently operating and instruments currently being planned and built. The coming decade will transform our understanding of the galactic center. The next generation Event Horizon Telescope and GET will add additional stations in Africa, Asia, and the Southern Hemisphere. The result: a substantially more complete interferometric baseline, enabling high-quality images on timescales much shorter than current full-night integrations. The primary science goal that motivates the InGet is the production of a time-resolved movie of Sagittarius A accretion flow, images separated by the SCO orbital period of approximately 30 minutes. Showing the evolution of plasma structures near the event horizon in real time. Gravity Plus, the planned upgrade of the gravity instrument, would extend its sensitivity to much fainter stellar sources, enabling the orbital monitoring of many more S-stars. The most anticipated Gravity Plus science result is the first measurement of the spin of Sagittarius A through the lens-throwing precession that a rotating black hole exerts on nearby stellar orbits. A measurement that would completely characterize the black hole's spacetime geometry and constrain its accretion history. In X-rays, the Athena mission, planned for the early 2030s, will provide spectroscopic analysis of SGR* flares with sensitivity and resolution far beyond anything currently available. The James Webb Space Telescope, already operating, contributes through its extraordinary mid-infrared sensitivity, probing wavelengths from 5 to 28 microns that are complementary to the near-infrared monitoring from ground-based observatories. By the mid-2030s, we will have a dataset from these combined facilities that is qualitatively different in its scientific content from anything available today, richer in time resolution, broader in wavelength coverage, deeper in sensitivity, and longer in temporal baseline. The questions raised by the 2019 flare will have answers by then, that ancient people named and mythologized and navigated by long before they understood what they were looking at. The Milky Way, our galaxy, our home, and somewhere in that band of light, hidden behind the dust, invisible to unaided human eyes, the center, where, right now, something is happening that has not been observed to happen in 20 years of careful, systematic watching. The photons that tell us Sagittarius A has brightened, the infrared photons that arrived at the NIRC Decameron on Ketu on the night of May 13, 2019, all left the galactic center 26,000 years ago. When they left, our ancestors were in the middle of the Upper Paleolithic. They were painting cave walls in France and Spain. They were following herds across Ice Age grasslands. They were, as far as we know, the first fully modern humans to look up at the night sky and wonder what the Milky Way was. They never found out. The photons from the galactic center generated during their lifetimes have not yet reached us. They are still 26,000 years away. The galactic center is not a static place. It never was. Long before 2019, the black hole at the center of our galaxy was doing what it does, flickering, flaring, occasionally brightening, occasionally dimming, responding to the ever-changing supply of material from the stars and gas clouds in its immediate vicinity. We missed most of it, not because we were inattentive but because we didn't have eyes. What we are witnessing now is the beginning of a sustained observational relationship with the most extreme environment in our own galaxy. The 2019 flare was not the end of something. It was a data point in a monitoring program that will continue for decades. We saw our galaxy's heartbeat differently. We don't yet fully understand why. But for the first time, we have the eyes to watch it happen. The Milky Way is looking back at us, slowly, 26,000 years of delay between event and observation. Obliquely, only through invisible wavelengths that our instruments can detect. Quietly, faint signals requiring the most sensitive instruments on Earth and in space to measure. But it is doing it, and we will not look away.